This is All White Breaking Mad, part 2 of the manganese 3 acetate coupling reactions. This one example is on making P2P. I can do it in 90 minutes. We're going to get into those instructions right now. Alright, so you can see I have the chemicals and the milliliters that you need, or grams, and the moles. You know, like this is 150 milliliters of benzene, that's 1.68 moles. 150 milliliters of acetone, 2.03 moles. This one, 13.4 grams, that's 0.05 moles. And this is the dihydrate salt, manganese 3 acetate, or manganese triacetate. It's not anhydrous. 250 milliliters of the acetic acid, 250 mils, it's 4.37 moles. And the P2P you get would be 1.34 grams, which would be 0.01 moles. Here's the molar mass of that and the density. Anyways, you would just reflux this stuff under an inert atmosphere. I'm going to get into the inert atmosphere at the very end. But here's a reflux apparatus. You'd have all your stuff in here. You know, you'd heat it up, right? You'd reflux it. You got cold water here, so anything that gets pulled away will condense and go back into the pot. And you just do that until you until your MN3 turns into MN2, right? One's brown and one's pink. So when the brown turns into pink, you know you're done, right? And it takes about 90 minutes to reflux it and be done, okay? Now, argon is an inert atmosphere, an inert gas. And you can buy tanks of them that are really expensive, but you can also buy little bottles for $15 a can, and they're on Amazon. They're basically, when you have wine, you open the wine bottle, you didn't drink it all, you want it to be fresh next time you use it. You buy this argon and you put the argon into the wine bottle, you know, with the wine, and then you cap it up once you get the argon in there and the air out. That way you can, you know, your wine won't oxidize. There's no oxygen in there for it to oxidize, so it'll stay nice and fresh. So basically that's it. 90 minutes, bam, you got your reflux down, your brown is turned into pink. Alright, that takes about 90 minutes. Next step is your reaction mixture is partitioned between 400 milliliters of ether and 250 milliliters of water. Basically what that means to me is that they get 400 milliliters of something that's non-polar, like ether, and 250 milliliters of water, which is polar. They mix them in with the reaction thing, mix them up, and it should form 2 layers. You know what I mean? The ether layer or the non-polar layer would have your product in it, right? So you use a separator funnel and separate off your hydrocarbon, right? Once you have your hydrocarbon with your P2P in it, then you would take that and wash it with 250 milliliters of water, right? Throw 250 mils of water in there with it. Shake it up, you know, let it, you know, open it up and let it bleed a little bit, shake it, let it bleed, shake it, and then let it sit there, whatever, 15-20 minutes, and it'll form 2 layers. Save your hydrocarbon layer and throw your water layer away. Then clean it twice with 250 mils of 5% sodium carbonate. Twice, or it can be bicarbonate. Basically, that's just, you know, helping to get rid of any acid that's in there, any of the acetic acid. It will neutralize it. Then take your, you know, separate it again because your sodium carbonate's in water, so you're going to have 2 layers. Get your hydrocarbon out and throw some drying agent in there, some anhydrous magnesium sulfate, anhydrous sodium sulfate, something like that. Let it soak up all the water, you know what I mean? Start up for a while, let it and sit for 20 to 30 minutes, an hour, whatever, and filter out your magnesium sulfate, and it will soak up the water. Next, it says to fractionally distill out your stuff. You know, you can have extra acetone in there that you can reuse, benzene, acetic acid, etc. Actually, the acetone and the acetic acid, that'll probably be in the water layer. So you would have gotten rid of that with these washings. But the benzene is non-polar, so it'll be in the, you know, it'll be in with your product. Wherever your P2P goes, your benzene's going to follow. Distill all that stuff out so you can reuse it. Now it doesn't say to vacuum distill the rest of it. It just says, and then continue to distill until you get your P2P. You'll have 40% yield, which is 0.134 grams. Wait, 1.34 grams, and that's the end of it. 40% yield is based on the Man-3 acetate. Now that I've gone over the exact instructions, I didn't actually go over the argon yet, how to use the argon. I'm going to do that at the very end. But let me go over some stuff about what I do not like about this reaction, the argon being one of it. That's why it'll be the last one on the list here. The first thing is this. I want you to look at the molar whatevers, right? Now remember, we need twice as much Man-3 acetate because it's doing two things. It's oxidizing twice, right? Keeps taking off a hydrogen free radical twice. To do that, you need twice as much Mn2, right? Now I want you to look at you got 1.7 moles here almost and 2 moles here. Okay, I could see that maybe a little bit. They're kind of even. Because you need a 1-to-1 ratio, so that's kind of good. This is the solvent. It's got twice as much. It's got 2. This has 4, say. I can see that. It's the solvent. This has got to be confusing now. You'll notice that there's only 0.05 moles of that, and you need twice as much. So if I take it in half, it would be 0.025 moles, right? Now, do you see the difference between, you know, this should be 1, 1, 1, and up here it'd be 2. But it's not. It's not. It's almost, say this is almost 2 and this is almost 2, so that's a 1-to-1 ratio. But look at this, 2, and then it drops down to 0.025. How many times more is that? Let me get a calculator. That's 80 times. They used 80 times more molecules than they used, you know what I mean? You need 2 molecules of this, 1 and 1. But we took that 2 in half, so it should be 1, 1, and 1, right? Instead, it's 1, 1, and 1/80th of 1. 1/80th? 1/80th. 1/80th, that's crazy. Why would they do that? I don't understand that. I understand that the P2P that you're making will be more reactive towards the oxidizer, right? Instead of making this into the, you know, grabbing a proton, a hydrogen off of here, a free radical, it'll take the free radical off of what you made. And now this will try to react with the benzene. Or this will try to react, you know what I mean, with itself or whatever. Yeah, it'd actually probably be, because this right here would be an alkyl group attached to it, say, and that is electron donating, so that would activate the ring. This would actually be more active than the benzene ring, so it would start reacting and try to add to another P2P ring. But, so I understand why you wouldn't add as much, you know what I mean? You don't want to make too much P2P because you'll start reacting with it, right? But 1/80th? 1/80th seems so low. That just seems crazy. Like, what's the point of even doing this reaction? So I would suggest, I don't know if this reaction works, I have no clue. When I try it, I'll probably use ethyl methyl ketone instead of methyl methyl ketone. You know what I mean? That way I won't be making P2P. I'll be making P2P with the methyl group right here on this benzyl carbon. I don't know, I'll have to look it up and see if that's illegal or not. But anyways, I would try it and see if it worked. If it did, then I would start trying to add more of this oxidizer. Because an 80-to-1 ratio, no. I would, the next time if it worked, I would double this. And if it worked then, I would double it again and keep doubling it until I seen that it was screwing up, you know, adding more is not good. Because 1 to 80, that's crazy talk. That doesn't make any sense. Keep in mind it may be about solubilities and having, this may be a solid in the reaction until someone actually does it. You don't know how much MM3 you can put in, the salt, how much you can put into the reaction. But let's just say I put 4 times as much as this, 4 times as much as these instructions. Everything else stayed the same, just the manganese 3-acetate I added 4 times as much, 53.6 grams instead of 13.4. And I got only a 30% yield. I would still get 4 grams instead of 1.34. Why wouldn't they do that? I'd rather have a lower yield and get 3 times as much as this stuff than, you know what I mean? Because you're using a lot of chemicals here. Let's say you added in 134 grams, a whole mole of this man 3-acetate. Okay, that's 10 times as much instead of 13.4 grams. Let's say your yield was only a quarter, 25% instead of 40%. You would still get 8.4 grams instead of 1.34. I don't see why you wouldn't try to do it. Even if your yield went down, but what you get in return is a lot more. I don't see why they would use this so low. But like I said, it may be about solubility and having solids in the pot that you can't put that much in, you know what I mean? I've never done the reaction, so I really don't know. Oh, the other thing I didn't like about it is this. The acetone is more reactive than the benzene towards this oxidizer. So the oxidizer is obviously going to react with the acetone. It's going to dehydrogenate. Then that is going to react with something. And what's in the pot? Acetone and benzene. So it doesn't have much choice, you know what I mean? So it has those 2 choices. So it could start reacting with acetone. You know what I mean? You make this into a free radical enolate, and it reacts with another acetone, maybe kind of doing almost like a aldol condensation reaction. I would think I would want to add, like they have more acetone than benzene. I would think that I would switch these around so that I had more benzene and less acetone. But that's just me. I mean, I'm just guessing about that. I don't know. It just seems like I would add more benzene than acetone. The other thing is that looking at these things, there's 150 and 150, that's 300 milliliters. 400, 550 milliliters, plus say 20 milliliters there, that's 570 milliliters. You're going to need a 2,000 milliliter round bottom flask to do this reaction to make this little tiny amount. Okay? So that doesn't make sense to me. That doesn't make sense at all. That you would add so little of this 1/80th when you need, you know what I mean? So I don't like those things that I mentioned so far, but it does seem like a good reaction. At least you can reuse, you know what I mean? You can fractionally distill at the end and get your benzene back and your acetone back and reuse them, you know what I mean? And then your MN2 acetate, you can get it back, right, in the pink form and just remake the MN3 acetate. So you can recycle it also. And you can recycle your acetic acid. So as long as you can re-up this to a better thing, 1 to 80 ratio is crazy. I mean, this is 1/100th of a mole, you can only do 1 reaction with this to play around with what you made, you know what I mean? Now as for the argon, this is another thing that I don't like, is the argon. Okay, well I ran out of time, so there's only one thing really left to talk about, and that's the argon. So I'll talk about that in part 3. So please don't miss part 3. You all have a great day, and always remember, science is great.